Okay, good morning. My name is Tarique Shakil or Tarique Shakil, whichever way is comfortable with you, I'm fine with it, no problem. I understand the UE at the end confuses people at times, right? So call me whatever you're comfortable with. I'm a principal technical marketing engineer with the cloud networking business unit. I've been with Cisco 11 and a half years as a permanent employee. Prior to that, I was a contractor with Cisco, and I used to teach. I was a technical instructor for TAC. So I used to run what we call the graduate apprenticeship program in Bangalore in India, where you take the new hires and you train them for 9 months, right? 5 days BGP, 3 days OSPF, things like that, depending on the team. So I mostly focused on routing and switching. Then I moved over to HTTS, high-touch technical support routing protocols. I spent 4 years there, mainly focused on service providers, troubleshooting all our global clients, core, edge, and some mobility. Then, the whole SDN thing happened, right? 2013, 2014, I was like, okay, I should get into don't want to miss the bus. So I was like, okay. So went into data center space. And then later I realized once I entered the data center space that everything I did in the SP is just ported over to the data center, right? All the technologies. The service provider was always a shared infrastructure, virtualized, multi-tenant, right? All those concepts. So I grew in the data center quite fast. I started with ACI first. This Nexus 7K, 5K, right? Lisp, VXLAN. Then the 9K platform got launched with ACI and NXOS. I worked with that. And I moved into CX product management. So a lot of you may be engaging with your CX engineers, but I was in the product management side. So just briefly, what we did in product management side is we interface with engineering. We take their products, incubate it in our lab, and then we also do the early field trials. So the first time adopters. So I got exposed to all the new products that came out of engineering, specifically the data center. Right, so I've been working with VXLAN and ACI for about 7 years now, since 2014, right? So I've seen both, I have expertise in both, right? Obviously, this session is specifically about introduction to VXLAN BGP EVPN. Sorry, I should have added that part at the end, right? But, so we'll look at, this is an introductory session, so I assume you have no knowledge, right? And I have 45 minutes to talk about a topic that I spend 50 hours per week training CX on, okay? So what I try to do is, I'm just sticking to the basics, the fundamentals, right? And I want to express it in a language that is easy for everyone to understand, right? And I will not use the word overlay and underlay till I actually defined it, okay? So how many of you are new to VXLAN, BGP VPN? Completely new, perfect. How many of you are exploring the idea of implementing VXLAN in your fabric, in your data center? Excellent. So what this session is going to do is broken up into this is the agenda. But if you look at the 3 questions that I'll be focusing on is, first, what problem does VXLAN actually solve? Why would I want to, what was the issue with the current data center architectures that we had to bring in VXLAN BGP VPN, right? No new technology is made just for the sake of making it. It's trying to solve a problem. So we're going to review those problems that existing architectures have had. Then we're going to look at, the second question is, okay, what is the VXLAN BGP VPN architecture? And we're going to look at it from a underlay, overlay, control plane, data plane, right? So we have 2 layers now. We have the virtual layer, virtual network layer, and we have the physical infrastructure layer, the underlay, right? So then the third thing we're gonna look at, okay, how does this work? At a high level, how does it work? And when I mean how does it work, how do we learn routing information and how do we forward it? And what is the role of VXLAN and what is the role of BGP EVPN and how do they come together? And that's what the goal of this session is, right? Does that make sense to everyone? And I will also end with a packet walk, and that's basically answering the question, how does it work? Feel free to interrupt, interject with any questions. And if I feel that your question could become a 45-minute discussion, I will answer it at a high level, right? And then we can definitely discuss offline, right? So please don't feel offended in any way that, sometimes there's more to it. For instance, the packet walk, I just define it at a high level, that this is a source destination. There are obviously other things in the packet, in the BGP packet, other attributes. We don't go into that, right? We have separate sessions for that, which I shared in the earlier slide. I'll dump it in the group chat. So if we look at the evolution of data center fabrics, we all are familiar with the STP-based. And when we look at these four, we're going to discuss each one of them. I want to discuss with you three aspects. The first aspect we want to discuss is how the endpoint information is learned, right? So if we look at the STP-based, we all know that at the access layer, we're going to have a layer 2 switch. Each access layer switch is going to connect to a distribution layer switch, and it's connecting via a layer 2 link. And we know that the moment you have layer 2 Ethernet and redundant links, spanning tree protocol kicks in, and we know that spanning tree protocol will do its job of blocking one of the interfaces to prevent a layer 2 loop. So here immediately you see that the layer 2 switches that attach to the endpoints are not the first hop gateway. The first hop gateway we see at the boundary, where you see the blue dashed line, is the layer 2, layer 3 boundary exists at the distribution layer. That's where the gateway exists. And what does that tell us? Because the gateway exists there, we know that IP forwarding happens there. And if IP forwarding happens there, we know that we're going to have ARP cache. We're going to have IP databases, and we're going to have MAC table databases. So it's concentrated at that distribution layer, right? But immediately you can see from here that one of the biggest caveats here is that you're not using all your links for forwarding traffic. If you move on to the VPC-based, what or MCLAG, as the other vendors in our industry call it, multi-chassis link aggregation groups, right? Arista and other vendors call that. What we try to address the problem of using redundant links, right? So if you go from the bottom, the layer 2 switch attaches to a group of switches, which we call a VPC domain. Essentially, from a data plane perspective, they're providing you active forwarding, but from a control plane perspective, they have individual identities, right? So what I mean by that is that if you're running BGP on both of them, they have a unique router ID. They're seen as separate, different routers. Now, the links between the access switch going to the distribution switch, you'll see that these links, they're still layer 2. But the way we overcome this limitation of having one interface blocked is by creating port channels here too, right? Because port channels allow us to aggregate the Ethernet interfaces to allow forwarding. But here, what we did is, here in this topology, you'll see that the distribution layer switch is still access the first hop gateway, right? The default gateway. So all your FHRP configurations apply here. Your HSRP, VRP, GLBP. You're limited to what? You're limited to these guys being the gateway, and therefore you're limited by just having a centralized anycast gateway, even if you use HSRP. All the IP forwarding will happen here. That means what? Similar to that topology, you'll be inserting your firewalls there, any sort of QoS policy. So what happens? The distribution layer becomes that central point of where all policies are defined. And therefore, when you want to upgrade, when you grow, you expand your infrastructure, a lot of times you end up scaling up. You ended up scaling up your distribution layer to support the growth of your endpoints and to support the growth of your network. Now we move down to Fabric Path. So Fabric Path is sort of now entering, evolving into the concept of locator ID separation, right? So have you guys heard of the LISP protocol, right? Locator ID separation protocol. I wrote a book on that. You can check it out on Amazon, right? So it's that same concept again, that these endpoints located are attached to the layer 2 switches. These layer 2 switches are identified by our switch ID in the fabric path. We're running ISIS now, right? ISIS on these links, intermediate system protocol, and that is a protocol that runs at layer 2, right? And what happens is that ISIS builds a SPF tree using in this cross fabric, and what it does is that it advertises the endpoints and their location, which is the switch ID of these switches attached to in a cross fabric, and it distributes it through link state advertisements across the fabric, right? So now what happens? In the ISIS database, all the switches have an entry of which MAC is attached to which switch. It's not a flood and learn mechanism of learning endpoints. Therefore, okay, that was an improvement in the sense that we're having less of flooding. We were not depending on flooding frames to learn endpoints. We have some intelligence. We've introduced an ISIS control plane, but remember what I told you, it only learns MACs. It only learns MACs. It only distributes MAC information, and therefore, the fabric path domains, the overlays are mapped to a VLAN. So 2 limitations, right? First, it's a layer 2 overlay. So if you want to do routing, you still needed to have a centralized anycast gateway. And we did try to address that problem in Cisco by having what we call HSRP anycast gateway up to 4, but that was a limitation, right? So then, so similar, but it did help us overcome the limitation of the redundant link being blocked, right? So now we have forwarding, but of course fabric path is proprietary, right? But of course the industry, open standard industry was of a similar technology was Trill, transparent interconnection of local links, right? That again ran on ISIS. So we move over to VXLAN flood and learn. Again, we have a VXLAN flood and learn is a flavor of VXLAN, the first layer that came about, that tried to solve the problem of having layer 2 extensions over an IP fabric now. You notice now that the layer 2, layer 3 boundary has now moved down to the access layer. Here, it was still at the spine layer. So what does that imply? That tells me that the links here are IP enabled. These are IP interfaces. That allows us now to have IP ECMP forwarding in the fabric. But again, VXLAN flood and learn, the initial release was simply a layer 2 extension that allow us to do bridging, nothing else. So then what? Same problem as the other ones. We still had a centralized anycast gateway, right? And the biggest drawback of this flavor was that, as the name implies, flood and learn, it depended on frames to be flooded through the fabric for the remote endpoints to learn about a particular endpoint and then populate its forwarding table to identify where that remote endpoint is connected and forward it. So we didn't have a control plane that allowed us to learn endpoint information. It depended on flood and learn, similar to the classical Ethernet, right? So we kind of went forward and back. We went forward in one sense because we now have an IP fabric, right? Not a layer 2 fabric. And we retained the layer 2 extension, the bridging functionality, but we removed a control plane. So the answer to that was finally we moved to the topic of today's discussion, right? But just to summarize, if we look at the data center challenges that existed in legacy architectures, we had rigid provisioning, right? Because again, the gateway was in a central location, and that's where the IP forwarding and decisions were made, and therefore all your layer 4/7 devices had to be connected into the central location. We had convergence time issues, as we know. Any time you have an interface with STP, link flaps, what happens? Right, remember those transition states that we learned in CCNA class, right? With max age time, right? Listening, learning, 52 seconds go by. We try to do rapid spanning tree, but at the end of the day, anytime there's an STP convergence issue, MAC table flushes, right? MAC table flushes. We have unused links, suboptimal forwarding. This reminds me of a story. Once I was introducing, this is 2006, I was installing a switch. I mean, lessons from the field. Fresh guy, CCNA, straight out of school, installed the switch in the network, and it was a Catalyst 2960X, right? Nortel networks were slowly introducing Cisco switches. That access switch became the root switch, right? And this is a semiconductor manufacturing floor, right? We had literally thousands and thousands of machines that were making chips and stuff. And what happened when the access layer switch becomes the root switch? What happens? All traffic forwarding path goes through that access layer switch, and I brought down the network, right? So placement of the root switch, very important, right? Very important. Now, broadcast storms, right? What did VXLAN do in that sense? It did help eliminate controlling of the broadcast storm to some extent. EVPN improved it further. No endpoint mobility, right? Application teams need the flexibility to migrate and move applications. Why? Because maybe the server has some resource issue. Maybe the switch that the server attached to is having issues, right? So we want that flexibility. And as the endpoint moves, we need to be able to have a control plane and data plane that is intelligent to immediately detect that move and ensure that there's no packet drops, right? So you may ask me, hey, the previous architectures, you have layer 2 extensions all the way. You can move. Yes, you can move. But is it efficient in moving it? Meaning that will there be packet drops, right? We want to minimize the packet drops. Scalability challenges, scale up versus scale out, right? We talked about the distribution layer, the centralized gateway. Anytime you want to grow your network, you're going to add more VLANs, central gateway, we need to scale up, right? Buy those expensive line cards and fabric cards, right? We know how cheap those are. Apex, CapEx, right? Expensive to upgrade. It's related to the previous point. And lack of elasticity. This last point has to do with the ability of the network to respond to the application team, right? I can't emphasize this enough. Every technology that we're moving forward, talking about cloud, right? The network team, the network infrastructure, the network technologies are being evolved to address that, right? And even as when I was a network consultant, if I'm in a 3-day workshop, right, I encourage you all to, when your Cisco consulting engineers come on site, bring in the storage guys, bring in the app guys, right? So that we don't get any surprises later. Do you know what I mean? Because the network has to support the application. When I was a consultant, 3-day workshop, I spent 2 days with the compute and app guys, 1 day with the network guys, right? The 1 day with the network guys. Because once we understand what you're onboarding on that network, we know how to architect it. So elasticity is what? The ability for the network to respond to the change of the requirements in terms of policy for the applications, for your storage. And that's where SDN came in, right? That's where we have the concept of a programmable fabric. As you move endpoints, we want to be able to apply policies on the switches according to the need of that application, right? Now, when we didn't have SDN, what did we do? We provisioned the same VLAN across all the access, right? We provisioned the same policies just in case we had to move the servers, we had to migrate the VMs, right? So that's what we mean by lack of elasticity, and the way we address that is obviously the SDN story. So we come to today's Cisco fabric technologies. There's ACI, and there's VXLAN BGP EVPN. Now, I cannot sit here and compare and contrast, because in CX, I do a 3-hour workshop just on that, comparing and contrasting the architectures of ACI versus DCNM, right? And I shouldn't use the word versus, right? Each of them have their place, right? Each of them have their plus points, right? And their usability. But if you just to go over ACI a little bit, ACI, first thing you notice, cross fabric, right? We want to have cross fabrics. Why? Latency in the network, right? We want to ensure consistent latency. One hop to go from one endpoint to the other endpoint. ACI is a VXLAN fabric. That's why the other reason I brought it up. It uses VXLAN in the data plane, okay? But where it differentiates, as I'll elaborate later, is that it uses different control plane. And what do I mean by control plane? Control plane is a protocol that we use to learn about network and location of endpoints. ACI uses Council of Oracle protocol, Cisco proprietary, okay? But fundamentally does similar things as Lisp, right? Same concept. It's a pool model. Pool model meaning that what? That all the endpoints will be known by the spine. The spine becomes that centralized database where all the endpoint information is learned. Whenever an endpoint wants to communicate with another endpoint, it will first resolve the location. This is one of the methods of forwarding, by the way. There are many methods. You can tweak the behavior, right? It will pull it, and once it pulls the location of the endpoint that it wants to communicate with, then it will encapsulate the frame and send it in a VXLAN frame. But the important thing for you to understand is what? It overcame the limitations, the challenges we talked about in many ways. It was programmable, right? It addressed elasticity. We have a layer 3 fabric that runs ISIS in the underlay, right? It runs ISIS protocol in the underlay, but a fabric path only advertised what? MAC information. It was MAC and MAC. This is MAC in IP UDP, right? So then we come over to VXLAN BGP EVPN. VXLAN BGP EVPN, again, is a VXLAN fabric, just like ACI, but it uses border gateway protocol, Ethernet VPN as a control plane, and that's what we're going to focus on in this class. Right? But you notice the architectures are very similar. Spines, right? We have layer 3 fabric, we have VTAPs, right? The gateway is now moved to where? The gateway is now moved out to the VTAP. And how the gateway works, we'll talk about it. But you'll notice that the fundamental role of the spine is going to differ based on the fabric technology. Any questions so far? Any one of you guys running ACI? Yes.
Is that Cisco's suggestion to run ISIS?
In ACI, you can only run ISIS. That's a very good question. But in VXLAN BGP VPN, you can choose your underlay. You can choose that. Do you want to run eBGP? Do you want to run ISIS? Or do you want to run OSPF? Right? So, did I address your question? Okay, thank you. So, but that's a very important question he asked there, right? And again, I told you that in ACI, you don't touch anything. It's a zero-touch provisioning. You answer 5 questions, your fabric is up. Okay, your fabric is up. You don't choose your underlay. You don't even choose your TEP IP. Your VXLAN fabric is up. But with VXLAN BGP VPN, you have that choice. You have that flexibility. So now I told you I wouldn't compare the two, but since you asked that question, just to end this on this. Now if you're an operations guy, right? You are currently a layer 2 data center. You come from the VPC world. You guys aren't too strong in routing technologies. You're not concerned with that. In fact, maybe you just need a fabric that allows you to interconnect hosts, so that my apps team can start onboarding their applications, right? And you need it to be programmable. ACI might be the way to go, right? Because operationally, it's simpler for you. It's much easier for you. But now if you're a person in an industry like service provider, where you like to have open standards, you like to control how your networking is going to work underneath, then you might want to go that path. So again, as I said, these are apples and oranges, right? It depends, right? Which way to go. But my main point here is that they're both VXLAN fabrics. They're both VXLAN fabrics. But the focus of this class is VXLAN BGP VPN. There are other ACI sessions. So before we get into VXLAN BGP VPN, we need to first understand this concept of network virtualization. And it's nothing new, right? It is nothing new for us. It's been around for 30 years. What's the first way we virtualized? At, say, layer 2 on a switch. Remember we had hubs before? And then what do? We introduced bridges and switches. And how do we segment at layer 2? We created VLANs, right? And then what happened? Especially in the service provider industry, as the service provider started onboarding more customers, they needed a way to use one router to share it across customers. And what did we do? We created VRFs. Virtual routing and forwarding tables. Those are routing tables that are independent from one another, isolated from one another. So what did a VLAN do? It isolated MAC tables, right? And what did VRS do? It isolated routing tables within the same multi-layer switch or router. So data center network overlays are building on top of that, So let's start looking at understanding the concept of underlay and overlay, because I will be using that word over and over again. If you look at this green box here, we have a physical infrastructure. You'll notice we have clearly edge devices with endpoints attached. I'm going to use generic terms right now, not VXLAN terms, just to get the concepts across. We have edge devices. Now, the edge devices is the point where the tenants are attached, or what we call the users. Now, these you can have multiple departments. If I use the word tenant, that can equate to, if you're talking about an enterprise, you may have segmented your network based on departments. Or if you're talking about service provider, you may have customer A, B, C, D, and you want to isolate their traffic in the data plane and control plane, so you put them into different VLANs, you put them into different VRFs. Okay, so on the edge device is where your tenant endpoints hang off. Your core device role is to establish network communication between your edge devices. That's it. So what does that mean? Each edge device will be identified by an IP address, and the core device will have the IP forwarding information to get to each of the edge devices. That's its role. So what does that mean? The edge device has no visibility, the core device has no visibility, no information about the endpoint IP and MACs. Why? Because its only role is to move traffic from edge to edge. Just like if any of you are from the service provider industry, right? You have MPLS, right? PE to PE, same concept. Core devices have no information about each customer network attached to your provider edge device, similar concept. So then, now these edge devices need to talk to each other. These endpoints, they may need to bridge, which means what? They're talking within the same network, or they may need to route, which means they're going across networks or across VLANs, right? So, what does that mean? Now, if this middle device doesn't have any forwarding information about the edge device, how do we deal with that? We build a tunnel, and that's what you see here, a red tunnel. And that red tunnel becomes our virtual network. It's a virtual logical network. This is nothing new. We've been doing this for 30 years, GRE, MPLS, right? And each tunnel was either created for the purpose of bridging or routing, right? So the other thing was that each of these tunnels, because we have a shared infrastructure, right? We want the ability to onboard multiple customers, multiple tenants, multiple departments, but at the same time isolate them. They don't even know they exist. We had to find a way to encapsulate or encode in the packets, control plane and data plane, tenancy information. What VLAN do they belong to? What VRF do they belong to? So there are three things in the overlay, three problems we address in the overlay. First is what kind of service does the overlay provide? Is it bridging or is it routing? And when I'm talking about bridging, it means what? We're communicating within the same VLAN, within the same subnet. And the second thing is, if we were routing, that means that we need a way for this overlay, this tunnel, to be able to go from one network to another network. And third, we need to be able to identify the tenant or the logical MAC table. In this case, remember when I create a VLAN, I essentially create an isolated MAC table. When I create a VRF, I create an isolated routing table. So these are the things that we need to, fundamental concepts that we need to understand with regard to underlay and overlay. And the last thing I want to mention is that the underlay or the transport network that is has routing protocols running so that you can establish those tunnels, right? We can establish those tunnels. If you don't have a routing protocol running right here between the edge and core devices, the edge devices will never be able to communicate with each other. So we have a family of protocols that run in the underlay for the edge-to-edge communication. Then we have a family of protocol that may run between the edge devices to communicate endpoint information. What endpoint information? What bridge domain does it belong to? What VRF belong to? What tenant does it belong to? So that's the difficult part here, because you got multiple layers of protocols interacting with each other. And this is the obstacle I faced when I first started learning these technologies. And it takes time, guys, okay? It takes time. Right, so to summarize, underlay is responsible for tunnel endpoint reachability, while the management of the virtual tunnel is handled by the overlay. Any questions? Oh, one last thing. Each service is identified by a virtual network. So the service, remember I referred to as bridging service or routing service. So we have an identifier to identify a bridge domain that is stretched on the tunnel, or we have an identifier that identifies the VRF that's stretched on that tunnel, right? So you will see these terms popping up. I want to give you examples of layer 2 and layer 3 overlays. So we have those of you who are coming from service provider industry, or maybe large scale enterprises that run their own MPLS backbone. If you remember, to stretch bridge domains, we had to use MPLS L2 VPNs, EOMPLS or VPLS. What did that do? It only did bridging. And we had to use different address families to signal those things in BGP. We had OTV. Some of you may have deployed that if you're longtime Cisco customers. What was that? That was, again, a layer 2 overlay. VXLAN BGP EVPN. We call it hybrid. Why? You'll notice it's in both boxes. It provides us integrated routing and bridging, meaning one overlay, one signaling protocol, one data plane protocol. You can do routing and switching. And that is a huge advantage. ACI is also a hybrid overlay, meaning that one control plane protocol, one data plane protocol, you can do routing and switching, right? So you can see that that's already a clear advantage. Lisp, it's a layer 3 overlay, only routing. Yes, sir? Right now, if you ask me, again, it depends on if you're already running a VXLAN fabric, VXLAN BGP VPN fabric. Ideally, you'd be advantageous to just extend the VXLAN BGP VPN, which we call that a multi-site architecture. You have the same transport protocol, same control plane protocol, operationally simpler for troubleshooting, managing, same type of configuration, right? So, did I answer your question? Oh, VXLAN. VXLAN. So now we'll look at VXLAN BGP EVPN architecture based following through and we'll relate it to the concepts that we learned about underlay and overlay. Now, if you see the name VXLAN BGP VPN, it almost sounds like a suite of protocols coming together, right? And that's exactly what it is, right? We have VXLAN, which deals with the data plane encapsulation or the tunnel encapsulation. And that's what we're going to talk about first. Then we're going to look at BGP VPN, which is the protocol that we use to learn endpoint informations from edge to edge. We knew that VXLAN operates over an IP fabric, an IP network in the middle. We have our edge devices. You'll notice that we have these color-coded hosts. Interpret that as hosts existing in different VLANs. VXLAN provides a way for us to interconnect and extend these tunnels, these layer 2 domains across an IP network. And how does it do that? You'll see that by encapsulating the inner encapsulation here refers to the original Ethernet frame. What does that mean? That means the frame that is being sent by the host. This part of the encapsulation we call the overlay, right? The overlay is what? The frame that comes in to the edge device coming from the tenants. A VXLAN header is appended. The VXLAN header will give us the information about the tenancy. What tenant does, what bridge domain, or what VRF these hosts belong to. The hosts that are identified in the source and destination MAC. The outer header, here we call the underlay header. The underlay header are the headers that will transport this frame through the fabric, IP fabric, hop by hop till it reaches the edge. And therefore, the source and destination IP information that you see here are going to be the IPs of the edges. And we'll look into this in more detail. But the main thing that the concept I want to get across to you here is that in VXLAN, we have an inner header, which we call the overlay header. We have an outer header, which we call the underlay header. The underlay header has information for you to route edge to edge once any frame comes to an edge device. The encapsulation that we use in VXLAN is what we call MAC in UDP/IP. Right? And the UDP header is part of the underlay. Any questions on, I will elaborate more with the packet walk, but I just want to get the fundamental concept across here that VXLAN is a tunnel that is formed between edge devices. It extends the layer 2 across an IP fabric. We have the encapsulation is broken up into two parts. We have the overlay, which is the original Ethernet frame coming from an endpoint, hitting a switch, and then we have the underlay, which is the IP. You have two namespaces. You have the inner address namespace, and you notice you have an outer address namespace. The outer address namespace is relevant only in between the edges, in the core part. The address space of the overlays are only relevant to the endpoints attached to the edge. Some important terminology you need to understand. A VXLAN segment is your layer 2 broadcast domain. So when we talk about a layer 2 broadcast extension, that tunnel that extends a VLAN from one edge device to the other edge device, we call that a VXLAN segment. How do we identify that segment, that bridge? Yes, sir. Sure. Okay, yeah. So now here's the thing. You could have in this case, what could happen is that generally what would happen is that when a frame comes from an endpoint, when a frame comes from the endpoint, it is stripped off. The inner header is stripped off. And then what happens is that it actually strips off the inner VLAN header, and you only send the IP forwarding information, right? But sometimes if you have a .1Q routed interface, it will attach outer VLAN header too. So we have VNIDs, right? VNIDs identify your VXLAN segment. We have VLAN, the term for an edge device in VXLAN is a VXLAN tunnel endpoint, right? Or the industry term is network virtualization edge. Each NVE device is identified by an IP address. So essentially what a VTEP does in VXLAN, it takes a frame, each VTEP device takes a frame as it enters an ingress port, maps the VLAN to a VNI, it looks at the destination MAC, sees where is the remote VTEP that destination MAC is attached to, encapsulates the VXLAN header with the VNI information, which maps to the VLAN, and routes it across to the destination switch. The destination switch then de-encapsulates based on the VNI information in the VXLAN header, maps it to the VNI, sends it out to the destination host. So these are the VXLAN benefits. I've gone over a lot of these already. The VXLAN provides you ECMP forwarding, the ability, it's an AL2 extension, so it allows you to have VM mobility. And we maintain tenancy, right? We isolate, we maintain the tenancy in the overlay tunnel. BGP EVPN is the signaling protocol that we have introduced with VXLAN. In the VXLAN RFC standard, it never standardized the protocol to learn endpoint information. It only standardized the data plane. So VXLAN MPBGP EVPN is an address family that is going to be running on the VXLAN fabric to advertise endpoint information. Which endpoint information? MAC and IP and tenancy. It also advertises network prefix. Where would we learn network prefixes? We will learn network prefixes from edge routers that come to a border device that will then advertise a network into the fabric. So if you look at VXLAN, BGP EVPN as a whole, the role of VXLAN is tunnel encapsulation, the data plane, while MPBGP is the control plane that will distribute the layer 2 and layer 3 information. Do you mind if we extend just 5 minutes? 10 minutes? Sorry, right? So now the BGP VPN is nothing new. I worked on it 13, 14 years ago with MPLS BGP VPNs, right? We took the same control plane protocol, and all we did is that we created a new data plane standard, which is the network virtualization overlay. That's where VXLAN comes in. But you'll see here, these are other standards for your information. MPLS BGP VPNs. Okay, so we took a technology that's been there for 10, 12, 15 years, took the control plane, tried and tested in the industry in a large scale, brought that control plane into the data center, but added a VXLAN header. We removed MPLS. Right, everyone clear on that, right? So the concepts of tenancy, how do we represent that? We represent it through two extended communities in BGP. One is the route distinguisher. So imagine, on the edge device here, we have multiple customers attached, or multiple tenants. They may use the same private IPs. How do I distinguish them? I'm just gonna append what we call a route distinguisher to the IP address. So I can have the HR department and the finance department in my data center using the same network, it's okay. We'll append a unique route distinguisher to the IP information that we advertise, and it makes it unique throughout the network into the BGP table, right? So that's the role of the route distinguisher. Route target is what segments the database into tenants. And when I talk about the database, I'm referring to the BGP table. The route target's job is to map to the MAC, what we call the MAC VRF or the IP VRF, right? Because remember, BGP VPN is sending MAC information for all your tenants, and it's sending IP information for all your tenants. And we want to be able to isolate them. How do we do that into individual tenants? We identify each MAC VRF or IP VRF with a route target. And the importing and exporting of route targets defines which information a particular VRF learns. Suppose I have a VRF HR and a VRF finance. VRF HR could use route target A. All the switches which have the VRF HR attached to them, we will configure a policy there to import all the network prefixes and endpoint information with route target A on them. It's a way to tag, to distinguish the tenant the endpoint or prefix information belongs to. Are you guys clear on the concept of route target and route distinguisher? Right, so route distinguisher is to distinguish the same network across two tenants, overlapping subnets, right? But route target is to distinguish distinguish a network learned information to a VRF, where it's going to get imported to, which table, essentially. Right, I'll just skip this for a while, right? But this is just examples of what a route target and a route distinguisher looks like. You can refer to it in the slide. Now I wanted to go over an example of what a configuration looks like. If we look at, we have a cross fabric, spine and leaf fabric. In the leaves is where the endpoints are attached, right? And first of all, look at the BGP global configuration. Remember, BGP EVPN is the protocol that is being used to learn the network information the prefix information that we learn from the outside and from the endpoints. To enable the BGP process, we do router BGP. We give it a router ID, right? Every BGP instance has to be uniquely identified. Each of these leaves will be configured to be a neighbor of the spine. The spine is the route reflector. Its job is what? Its job is to take the endpoint information, the network information from each of the leaves and reflect it out to the other VTAPs. Right? Why do we do that? Because so we don't have to have full mesh peering between all the leaves. We enable the address family L2 EVPN. Right? What is that doing? That's in multi-protocol BGP, enabling the EVPN address family. That's what it's a multi-protocol BGP. You can consider an address family as the type of information BGP can distribute. So when we're talking about EVPN, we're saying we're going to send MAC and IP information. And that's the purpose of the EVPN. Now, we also need to tell BGP, yes, ma'am. We also need to tell BGP to create databases so that it can store the various VRF information from each of the tenants. And that's what we're doing here. And we're going to be advertising both IPv4 and IPv6 information. Send community extended is important because information like your route target and route distinguishers cannot be distributed in an EVPN update if you don't enable extended communities. Now, that was just the global BGP configuration. Now, most of the complexity of VXLAN BGP VPN, the configuration happens at the VTAP. Why? It's the gateway, right? It's the gateway. It's where the endpoints connect, and it's where we're gonna identify which tenant an endpoint belongs to. So if you see, the first thing we're gonna do is, and the other thing is, each of the VTAPs is where the tunnels are sourced and terminated. So we have two things we're majorly looking at. We're looking at the creation of the tunnel configuration, and we're looking at the network virtualization related configuration. Every VTAP, we have two forwarding tables, MAC and routing tables. MAC tables are for bridging, routing tables are for routing. Now we have multiple tenants attached to them. So what do we need to do? We need to first segment our routing tables. And we create a VRF by the VRF command. We create EVPN, we create a MAC table for a particular VLAN, for a particular MAC VRF using the EVPN command. And each of these instances will have a route target and a route distinguisher. The VLAN command here will be allowing us to map the VNI. Remember, VNI is what we use as the identifier in the VXLAN header. We need to map it to a VLAN. And we do that here. So if you see this example, host 1 is in VLAN 10, host 2 is in VLAN 20. We need to map it to a VNI, and that's what this command does. We need to also create a VRFs. That is the routing functionality. And we segment the routing table by also, again, creating VLANs and creating L3 VNI segments. Right? Because here we're dealing with integrated routing and bridging. Each of the hosts need a default gateway. The default gateway will be configured on the VTAPs, and they are associated with a VRF. Here we see VLAN 10 is associated with VRF red, while VLAN 20 is associated with VRF blue. The interface NVE command creates your VXLAN tunnel. NVE full form is Network Virtualization Edge. And what we do here is we associate each VNI to the NVE interface. Notice that we source the tunnel using loopback 0. This loopback 0 reachability is going to be addressed by who? The underlay. So here with this command, member VNI 50,010, what I've done is I'm telling the VTAP that when you receive a frame with VLAN 10, map it to VNI 50,010 and send it, tunnel it across. We do the same with the VRF. With VXLAN, we have distributed anycast gateways. We're distributing the gateway using the same MAC address. And that makes sense because the gateway MAC is local to each switch. And this is what we call, and the way we configure that is on every VTEP, we go and define a common anycast gateway MAC. And we enable fabric forwarding mode anycast gateway that essentially tells each VTEP that, hey, if any endpoint resolves your MAC for the gateway, send this MAC address. It's common across all. So what does that do? When you do a V motion from one VTEP to the other VTEP, it's always going to use, in this ARP cache, you don't need to update it. It's going to be using the same gateway MAC all the time. This is the last section. I'll just quickly do a packet walk. So first thing we need to do is these endpoints need to be learned. Who's responsible for learning the endpoint information? BGP EVPN. BGP EVPN running in all these VTEPs and the spines, right? As a host comes up and sends a frame, it learns about it using this, looking at the source MAC, just like a traditional switch. It identifies the VLAN the host is in, maps it to a VNI, generates a BGP update, sends it to the route reflector. The route reflector reflects it to the other leaves, the endpoint information. So it does that for every endpoint. Notice here we have virtual switch also. Right, so you can have virtual machines, they send traffic to a physical switch, it'll look at the source MAC, perform the same operation. So this is a generic overview of the table of what it'll look like. So you'll see that each VTEP learns the MAC and IP, VNI, which is what? The bridge domain that it belongs to in the VXLAN fabric, and the next hop. The next hop is what? The IPs of the VTEPs it needs to reach to get to those endpoints. So if you just look at this, VTEP 1, to get to MAC B, IP B, I need to go to V2. Now, all of you have probably heard of ARP. Every time you're communicating within a VLAN, you need to resolve what? The IP to the MAC. Now, I have to inform you that BGP EVPN advertises MAC and IP information, and you may be wondering, can I use that information to optimize ARP in any way? And yes, we can. So now that we have the ARP in the BGP EVPN table, we have the MAC and IP information, we can download that into the ARP cache so that when host A, let's say a host A here sends an ARP request for IPB, they're in the same network, right? What's going to happen? Since V1 knows about IPBs and its MAC, it will respond as though it's host B. So it sends an ARP reply back to host 1 saying, hey, I'm host B, here's my MAC that you're trying to resolve for the IP. So we call this ARP suppression. This is different from proxy ARP. What does proxy ARP do? The gateway sends its own MAC, right? This is ARP suppression. The gateway is sending the MAC of the remote endpoint that the local endpoint is trying to communicate with. Now, how do you handle silent host? That may be a question that people ask, right? So now an ARP request goes across from IP A to host A. But what happens? I don't have an entry. V1 does not have an entry. Why? This is silent host. So what do? We flood it, just like that happens in a traditional network, right? When any frame enters any traditional switch, it doesn't know the destination MAC. What does it do? Flood within the VLAN. But here we flood it within a multicast group. And a multicast group is mapped to a particular VNID, as I showed in the previous configuration. So every time you configure a VNI in each one of these switches, it joins that multicast group. And that purpose of that multicast group is to receive BUM traffic, broadcast, unknown unicast, multicast traffic, right? And so what happens is that the ARP request goes across, the ARP request will go across in that multicast group, reach all the leaves that have that VNI configured, similar to a traditional switch. All the switches that have the VLAN configured will receive the broadcast. And then eventually gets to V2. V2 will flood out that multicast, that broad ARP request to the host B. Host B will send an ARP reply. Then what happens? When host B sends an ARP reply, it will then unicast it back to V1 because V2 already knew about host 1. Why? Because when it came up, it wasn't a silent host. BGP EVPN advertised it to all the hosts. So the ARP reply was able to get unicasted back. So let's look at 2 more examples, bridging and forwarding, and then we'll be done. So let's assume that we have a host A that needs to send a packet to host B, right? Host A is attached to VTEP 1. It will have a source MAC of source IP of IP A, destination IP of IP B, assuming they're in the same subnet. Remember, we're bridging. The source MAC will be MAC A, destination MAC will be MAC B. It hits the V1, the VTEP. The VTEP sees, okay, I know what VLAN you're in. That VLAN maps to a VNI 30,000. You're going to MAC B. MAC B also maps to 30,000. Oh, I need to bridge. Okay, now where's this MAC located? It's located in IP VTEP 2. So what does it do? It encapsulates the frame. So let's look at what the frame looks like. The frame, remember the overlay is what? The overlay is the original frame that V1 received from host A. It's got the IP of A, right? Destination IP, oh sorry, I went to the routing one, my bad. Sorry, there's a bit of a delay here. Oh. Yeah, sorry, they cut me off, my bad, sorry. But if you, apologize about that.